or minimizing the loss function. So it's decision trees, and it's the beginning of a kind of a very successful models. Now I hear music. What's going on here? Is that
Yeah, I think mute people so that there's no music. Okay, now I think it's good.
Okay, all right.
I'll mute myself as well.
Okay. So I'll start with the simplest one of these model decision trees, and then next time we'll talk more about some of the what's called the ensemble methods based on decision trees, and there are a number of them that are bagging and random forest, and some of the boosting methods also based on trees. So a decision tree is a very simple model. It takes so it's a classification model. We want to send a data point and into a category. We want to decide what category does belong to. And so a decision tree is a model that takes a data point and sends it through a sequence of yes and no decision nodes. And depending on what the answer is at each node, it will send it to one to the left or to the right, and it'll continue until it ends up at some category, or we decide that we have gone far enough. So here's a very, very simple example. So suppose we have just a data vector with two coordinates, x1 and x2. And the first question we could ask is the first coordinate is x1 bigger than 2? If it's bigger than 2, we'll go in one direction. If it's less than or equal to 2, we go in another direction. So if we go to, say we decide it's bigger than 2, then we can ask the next question, is x2, so the second coordinate, is that less than 1? And if no, then we can ask the next question, is x1 bigger than -1? And that way we sort of make a tree. So let's see how it works and how it looks when we draw it. So here's our questions. We start out with the first question, is x1 bigger than 2? If it is, then we go down to this node here. We call these branching points, we call them nodes, and we ask another question, is x2 less than 1? If it's yes, we end up in category 1. If it's no, so if x2 is bigger than or equal to 1, then we end up in -1. The other branch or the other side of the tree is that if x1 is less than or equal to 2, well, then we go down this path here, and we have a question here, deciding which branch to take. And this way we can divide our data points into, in this case, two categories, those that belong to category 1 and those that belong to category -1. And it's simply by taking an arbitrary data point and send it through these questions here. So again, this will take any point in R2 and it will put it into one of the two categories. So we know that means that it divides the plane into two separate parts, those that belong to +1 and those that belong to -1. And in this case, this is going to look like this. So it's going to be divided into these two parts here. Here's the -1 part, and the +1 part will consist of this part and this part here. So this is in all its simplicity what a decision tree, how a decision tree works. the question is, how do we construct a decision tree? So if we have a data set, or we have a supervised learning problem, where we have a data set where we have labels given to us, how do we construct a tree to fit these data? And so, yeah, let me just also, before we go on to that, note that a decision tree can classify multi-category cases, and it can deal with categorical data, so it doesn't have to be just numerical data. But it's a very, very versatile model that can deal with a lot of things. So if we have constructed a tree like this, where we can send an arbitrary data point through all these nodes and end up in the what we call the leaves, or the terminal nodes of the tree, and that will then decide which category a given data point belongs to. But the question is, how do we construct such a decision tree? So if we're given a training set, that means a labeled training set, then we have to figure out how we fit a decision tree to those data. So the general situation is, we're given a set of labeled data vectors. The data vectors are the first ones, and the labels here are the second part here. And we have these categories y1 up to yk. And now we want to try to make a tree that is going to fit the data set, in the sense that it's going to send the data points we have here to the correct categories. And then we can use this tree to actually categorize any data point. So we do this sort of inductively. So let's assume we have constructed a tree up to a certain level, and we're now at some in the tree we have constructed so far. We're at a terminal node. So we are at a node where we want to decide what we're going to do at this node. So we're gonna take this node, and we're gonna split it in two. We're gonna go in two different directions. So how do we split the node, or what does it mean to split the node? Again, what we're going to do is we're going to ask a question: is some coordinate bigger than or smaller than a given number? And then deciding on or depending on what that coordinate is, we're going to decide which road to take from there. So let's see what happens as we go down the tree. Right, we're gonna get our data set is going to get reduced, because we at each node where we go two separate ways, our data set is going to be split in two. And so when we've gone down a number of nodes, then we have reduced our data set. So at this particular node we are now looking at, we have some subset of our data that has survived down to this node. And so we're going to decide how we're going to split this data set into two subsets. So let's introduce some numbers here. That M be the number of data that are in this node we're looking at. And so for each category, so we have a subset of our original data set, and there will be some different categories. So some will belong to category Y1, some will belong to category Y2, and so on. And so for each category, Yi, we let Mi be the number of data points which has this label. And so when we sum up all these MIs, of course, we get the total number of data points. So we're going to introduce what's called a purity impurity measure for this node we're at. And so let's introduce some other numbers. We take these, the MI was the number of data points belonging to category YI, and let's take MI divided by M, so the frequency of YI, the number of the fraction of points that belong to category MI. And we can look at the most common category that occurs. So that will be the category which has the largest of these frequencies, largest of these PIs. And we can then define an impurity measure for this node. We can look at what's called the misclassification error. So that is the number, the sum of these PIs for the i's different from J. Again, J was the most common. So that's 1 minus PJ, because of course all the P's, they sum up to 1 because of the sum of the MIs is equal to M. So this is one measure. It simply says how many are not in this majority category. So this is something that measures how many other categories are present in this data set. That's not a very good measure, but some people use it. Some of the two other ones that are much more useful are what's called the Genie Index, where we take these PIs, and then for each PI we take PI multiplied by 1 minus PI and sum all of these up. And you can see that suppose there's just one category, so suppose all our data points of this node belong to one category. So there's just one category. That means there's just one PI, and that PI is equal to 1, because there's just one category. So that means that this number here is 1 for this category, and that means that this number here is 0. So if we're at a node which is pure, meaning that there's only one category, then the Genie index is 0. So another one is the entropy, which is also very useful, and that's defined this way, and that has the same property. If the node is pure in the sense that there's just one category, then PI is 1, and so log of PI is 0. So the entropy is also 0. So both of these are sort of measuring how messy the data set is, how many different categories are represented in this data set. Of course, we would like to sort it out into where all the data points belong to one category, right? So we're going to sort them into categories. So we can use these indices to decide how we're going to split a node. So if we have a node that's not pure in the sense that the Genie index or the entropy are not 0, then we're going to try to split this node into 2 nodes, and we're going to do it in such a way that we minimize the impurity index. So let's deal with the Genie index here. That's I guess is the most common one. So we have our node, we have the data set in that node, and we're going to decide how we're going to split this node. So let's say we're here, and here we have our data set, and they belong to different categories. And how are we going to split this node into 2 new nodes like this? Well, we're going to do it in such a way that we minimize the impurity index we get by doing this. So let's go to let's split it in some way, and that means that the data set is going to be split into two subsets. For each of these two subsets, we can compute the Genie index, and then we compute the weighted sum of these indices. We take the total number of points in the data set here to the left, the total number of points in the data set here to the right, and then we compute the fraction, the number of these. So these are the fractions here, ml divided by m. That's the fraction of data points that went to the left node, and mr divided by m is the fraction of the points that went to the right node. And for each of these two nodes, we can compute the impurity, and we look at this weighted sum of the two impurity measures. And then we're going to split the node in such a way into these two child nodes in such a way that this number here is minimal. Of course, this can be done in many different ways, and so it's not so clear how we do this. But it's let's do it with an example and see exactly how it works. So here's the example. We have this data set here consisting of 7 points, and there are 3 categories. I'll go to the board in a little bit because I've drawn it on the board. But let's just look at what the Genie index is for this whole data set. So we have to compute there's 7 data points. There are 2 points that have label 0. There are 3 points that have label 1, and then there are 2 points that have label category 2. So there are these 3 categories: 0, 1, and 2. 7 data points. So the proportions are P0, the number of points with level 0 divided by the total number of points is 2/7. P1 is 3/7, and P2 is 2/7. So the Genie index, well, that's by taking P0 multiplied by 1 minus P0 plus P1 times 1 minus P1, and P2 times 1 minus P2. And if we compute that, we get the Genie index is 32 divided by 49. So so we're gonna now split this. So this is the sort of the top node of the tree. This is the root of the tree, if you want to. So the trees are growing downwards here. So it's sort of the root of the tree, and then we're gonna branch out from this tree. And so we're gonna figure out how we're gonna split this. And now there are different ways of doing this. We don't want to split exactly at a coordinate that appears in these points here, because that would mean that this point is going to lie on the decision boundary. We'll see what the decision boundary we get in a little bit. But we don't want to split it in exactly at one of these points here, because they would put this point at the boundary. We sort of like to have our data point sitting comfortably inside the respective point, the respective parts of the space that we divide. We divide the space into these categories, and we want our data points to sit sort of comfortably inside those subsets, not on the boundary. So because then we don't really know which of the two categories they belong to. So we don't want to split at the coordinates of the data points. And so instead we want to split it at the midpoints between coordinates. So we're going to compute all the midpoints of the coordinates, and then we're going to throw out those midpoints that occur as coordinates. So let's just try to say that we propose our first split at x2 equal to 2.5. So we're going to split our data set into two pieces, namely those where x2 is less than or equal to 2.5 and those where it's actually bigger than x2 is bigger than 2.5, not bigger than or equal to. And so we can see what that gives us. So we're going to look at the points where x2 is less than or equal to 2.5. So that gives us this point. It gives us this point. It gives us this point. And it gives us this point and this point. So we get the left node is gonna contain these now. Your pictures is blocking it's blocking one of my points. But we end up with the points where what we had 4, we have 3 and 4. So we end up with those where the second coordinate is less than or equal to 2.5, and that's the 5 points we have here. And then those points where the second coordinate is bigger than 2.5, that's R, and that's the right node here. So that's these 2 points here.
So one question is, earlier you said that normally we would like to split at the midpoints between the coordinates. So x2, if I look at the midpoint of x2, that should be like somewhere around 1.5, right? If I sum like 2 plus
but we don't exactly know we don't know exactly where to split it.
Okay.
But we don't want to split it at coordinates that are coordinates of the data points, because that's going to put the data point on the decision boundary, and that's what we don't want. So it's a little, it's not, I mean, 2.5 is a midpoint of two coordinates, right? It'll be the midpoint of
the first 2 points.
This one and this one, right?
Right.
So that would be a midpoint, and it's not a coordinate of any of the data points.
Okay.
So there will be a possible candidate for a split here.
Okay.
So we will see what we get if we split here. Then we have to compute the Genie index, and so if we look at the L, the left node, there we had these 5 data points here, and we had the 0, 1, 1, 1. We had 1 of the points was category 0, 3 of the points were category 1, and 1 was category 2. So category 0, there are 5 points, 1/5 times 1 minus 1/5, that's 1/5 plus 4/5. Category 1 would be 3/5 times 2/5, and category 2 would be 1/5 times 4/5. Altogether, we get the Genie index of the left node would be 14/25, and the Genie index of the right node would be just 1/2. And also compute that. So we have to compute the weighted sum of these, and so the left node had 5 data points, so we get the weight 5/7 times the Genie index. The right side, the right node had 2 points, so the weight is 2/7. So we get 2/7 times 1/2, and so we get that the weighted sum of the Genie indexes is 13/20. So that's not for sure that that's the best possible. So let's write a little code and see how we do this. So first, let's write some code here where we can compute the Genie measure, the Genie index. So that's very simple. let me go to the code here. So here's the code that is just first to compute the Genie index, and then here's a little thing to compute the optimal split. And what is this noise for? Is that me? Is it? Oh. So the optimal split, again, what we're going to do is we're going to look at all the possible splits that we can make, and for each of them, we're going to compute the Genie index, and so we're going to compute first all the midpoints here, and then we're going to throw out those midpoints that are actually coordinate points of the data set. And then we're going to look at all the possible splits that we can make here. And for each of them, we compute the this weighted sum of the Genie indices, and then we're going to look at all these possible splits. So for each split, we're going to compute the Genie index, and then we're going to put those in an array, and we're going to sort it by. So we're going to for each of these, we're going to compute the Genie index and where we're going to split it. So we're going to, for each possible split, we're going to compute the Genie index and the place where we split it, and we're going to put that in an array that we're going to sort depending on the Genie index. Of course, we want to find the split with the smallest Genie, whether weighted sum of the Genie indices are the smallest. So here's our data with the labels are those that we have here: 0, 0, 3 of the ones, and 2 with twos. And let's just see how it splits that. And so I haven't, you can take the maximum here, but I have actually looked at because there are several that have the same Genie index. So here's one. The one means that so the coordinates are labeled 0 and 1. So 1 here, that means it's a second coordinate. And we can split it at the second coordinate at 0.5, or we can split it at the second coordinate at 3.5, or then it's the same thing comes back here, or we can split it here at the second coordinate at 0. So let me go to the board and okay. And let's try to do this. To do this here, I drew here my data set here, and so the first split was at x2 equal to 0. So that's that is just the x-axis here. So we can see that divides the data set into 2 pieces, one down here and one up here. There are 6 points up here. Here, there's just 1 point, so that's automatically pure. So we're not gonna deal anymore with this. This is already pure. This is Genie index 0 here, so there's no more splitting here. But up here, we can see what we're gonna do next in our data set. So we have we can compute the nodes that appear in in the two separate things. So the left node is just a 1 point. The right node here, we get these 6 points here. And so we can again try to compute the split. And if I do that, I get that the best split is that x2 equal to 3.5. So that would be 1, 2, 3.5. That will be up here. So again, we have split this into two pieces. This one here just has 1 point in it, so this is automatically pure. And then we have these 5 points in here. So we can again look at these 5 points and split that. And then we get the best split is that x2 equal to 2.5. So that would be here. Again, this one, now we only have these 4 points here. And so we do this again for these 4 points. You can follow along and run the code if you so desire. But here we get that the best split is coordinate, the first coordinate at 1.5. So that means we are here. And then we have 1, 2, and this is pure here, and we have these two, and that we can of course split in by splitting here at the first coordinate equal to 0. So what's our decision boundary? Well, we have the points that are in category 0. Those are the blue points. They are in this piece here. Then we have the red points. They are in these two pieces here. And then we have the green points, category 2. They're in these two pieces here. So our decision boundary, or the way we've split the plane into 3 different pieces are, actually this is not right, this should be this one here. So this is what the decision boundary looks like. We have a 2 pieces here. Those the category 2 points will be either up here or down here. The category 1 points will be, they will have x coordinate bigger than 1.5, and they'll have y coordinate smaller than 2.5, or they'll have y coordinate smaller than 2.5, and they'll have x coordinate less than 0. And then finally we have the category 0 points in this T-shaped region here. So this is what the tree, the optimal tree, that what we get by fitting this data set here. So so this is well, this is a lot of work to work out if we have to code it, but it's let's just see what we get here. So this is the oh, yes. Is this Yeah. Okay. Did you see what was going on at the board, or was that? Did you see the board?
Yeah, the board was
Yeah.
pretty
Okay.
obvious.
All right. Okay. Good. Okay.
So, Professor, I'm trying to understand, like, it's still not clear. What's the concept of impurity, right? Like, what is Genie Index exactly telling us? I'm not very sure. I understood what you explained on the board, but how it's translating in terms of Genie Index is not very clear in my head.
Well, the Genie Index sort of tells us how messed up the data is at each node. So at a node, if we look at the Genie Index, it tells us how messed up is the data set. So we'd like to have the data set to be all one category, right?
Right.
So it sort of measures how far away are we from being just one category. And so we always want to make it, as we saw, if there is just one category, then the Genie Index is 0.
Right.
So that's why we're trying to lower it. Every time we split at a node, we lower the Genie Index and make so hopefully at one point of time we get to 0.
Right.
Okay. And that's what we got here, where we get to when we get to the end here, all the nodes have Genie Index 0. Well, let me show you the tree here that we get here. So here's sort of what the tree looks like in terms of the data sets. On top here, we have the full data set. Now here I split it actually at x2 with 0.5 and x2 0.5, but we can split it. It doesn't matter. We can split it at 0.0 here. So if you split it here, right, you can see here we get one. This is pure. Right. This was just 1 point here. Then we have the rest of it is here. That's these 6 points. Then we split it again at 3.5, and we can see here now we get at the right node we just get 1 point, so that's pure. At the left node we have these 5 points. We split it again. We found again that the split was 2 x2 2.5. We split it. The right node is pure 3 point. It's just one label, and then the other one has 4 points in it. We split this at x1 equal to 1.5. So there we can see now we split it into two. The data set gets split into two pieces, both of which have 2 points in it. But this data set here on the right node here, this has 2 points, but they have the same label. So the Genie Index here is 0. So that means we have constructed a pure node here. This one here is still not pure. That there's one that has data that has category 0 and one that has category 1. If you split it at x1 0.0, then we split it into two pure nodes. So that's how it works here. We try all the possible splits, and we find the one that lowers the Genie Index the most, and then we keep going like this. So if we look at the classifier as we would use it to classify points, then we would start asking the 0 here. We start by asking, taking an arbitrary data point. We start asking, is x2 less than or equal to 0? If it is, then it's categorized as label 2. If it's not, so if x2 is bigger than 0, then we go to the next question. Is x2 less than or equal to 3.5? If it is not, well, then we're already in label 2. And so on down the line here. You can see we can go down keep asking questions. Eventually, each point will end up in one of these leaves here in one of the terminal nodes, and that'll tell us what category we want to put it
So
in.
I have a question here. Like, as long as a terminal node got only one data point,
No,
the
it can have
impurity
more.
will be zero.
It has to be pure.
Yeah.
It can have many data points, but they all have the same label.
But let's take a case where like all the labels for each data point are different, right?
Okay.
So I'm just saying that it doesn't matter how many times you split, but as long as each terminal node got same category,
Mm-hmm.
the Genie index will be zero, and so the impurity of the tree will be zero.
Right. Mm-hmm.
But then the tree may get very big or overfitted because we have cut it so many times, we have split it so many times that.
Yes, that's a very good question. Exactly. That's why you don't normally you don't. You can sort of figure out how many nodes, how many leaves you get, because if you keep doing it, you double the number. Well, you don't double, but it grows. The number of leaves grows pretty quickly with a number of data points. So you have to do different things there. You don't want to construct a tree where you get to full purity. You're going to have to decide when am I going to stop and whatever. And that's you have to do that in the software. So again, here's just the partition, and here's the how you do it in Scikit, because the SKlearn can of course also do it. So it's just SKlearn.tree and decision tree classifier, and it will just, you take the data and the labels, but you can put in different things in the constructor here of the tree, and you can see here some of the criterion is Genie. You could put in, but you can also put in a max depth, and max depth that will limit the how far you're going to go down the tree. Here it's only a small data set. We don't have to limit it, but if you had like 10 million data points, then you would definitely want to limit this. There are other ways you can do this. Here's just a picture of each. So in SKlearn, you can also make a picture of the tree you get, and so this is the tree here. You can see this tree here is like it's exactly the same one we got here. It splits at x1 is 0, and it splits in these nodes. It splits at 3.5 and 2.5 and x0 1.5. So this is exactly the same tree that we got doing it by hand. And here's a little code that constructs the or shows the decision boundaries and the way it splits the plane into regions. So that's using some software that's called GraphWiz that is also you can install, and that will draw these. That GraphWiz will draw the picture of the trees. So let's just try another little more complicated.
Can you go back to the previous slide? I just want to see the one where the Genie index was plotted. Okay. Before
that was this one, yeah.
Yes.
Mm-hmm.
I thought like it's not necessary that as you go down the tree, the Genie measure will go down, because it goes first, it drops from 0.653 to 0.611, then 0.48, 0.375. Then it goes back up to 0.5. So it's not necessary that it will always go down.
No, I mean not necessarily, because I mean if you have a data set with 2 points, one of each category, right? Then the Genie index will be a half.
Okay.
But if you have one of three, where you have 3 points and two of one and one of the other one, then then you'll have a lower Genie index. So the Genie index
Excuse me a second.
um,
In the example where the Genie went up, the other one, the Genie is 0. What's always the case if you've done a maximal split is the total Genie.
yeah, total
gone
Genie
down.
will go down. Yeah, the weighted sum of the two Genie indices will go down.
Always goes down.
Yeah, all right. That's otherwise you're not splitting.
Oh, so the weighted sum of the two Genie will go down. So if I put the number of points times this and this, okay.
Because otherwise you wouldn't split it. I mean, if you can't lower the Genie, the combined Genie index, you wouldn't split it.
Okay, right, correct. Yeah.
Yeah. So let's just try an example where we have a more complicated data set. So the code is here. So this is where you have a data set that looks like this. So this is a data set with two. There are only two labels, but again, it's not something we can split linearly. But the decision tree can split this data set. So we get just this rectangle here in the middle containing the points inside the circle. So for the decision tree, the decision boundaries will always be sort of line segments that are parallel to the axis. So here, right, these two are parallel to the x-axis, and these two are parallel to the y-axis. So that's a feature of the decision boundaries you get from a decision tree. They're always parallel to the axis. But you can make very complicated decision boundaries that way. I mean, it's just sort of piecewise a line, a piece of line. So this is the decision tree for this example here. So you can just take the data and fit the tree to it, and then get GraphWiz to draw the tree. So as I said, when we have larger data sets, we don't carry the process all the way through to get terminal nodes. So that could make enormously big trees, and that would not fit in the memory. So we can do as they do in SKlearn, that we can decide how deep our tree is going to be. We can set a limit how deep is going to be. Another way which SKlearn unfortunately cannot do is to get a tree, to make a tree that you sort of carry some path all the way to the end, and then you try to prune it. You eliminate some nodes and some branches so that you get a smaller tree. That's the pruning algorithm. But SKlearn unfortunately can't do that. But it requires a lot of memory to do that. So maybe it's okay. So in SKlearn, what you do is you limit the depth of the trees. So decision trees are the basis for a number of other algorithms. Some of the called ensemble algorithms and boosting algorithms. So the simplest example of an ensemble classifier is what's called bagging, a bag of trees. So again, if we have a training set with n data vectors, then we can draw samples with replacements. So we can draw many samples with n elements, but where they're repeated elements. And for each sample, we can fit a decision tree just the same way as we did before. It doesn't matter that some of the data points are repeated. That's not going to make any difference. And then we'll get, as many times as we sample, we'll get a tree to predict the category of some out of sample points. We just send it through all these trees, and then we take so each tree will determine a category. And well, we should say here, what do we do if we don't have a tree where all the terminal nodes or all the leaves are pure? well, then of course we assign the category, the maximum category or the most common category of that. So if we have a node that has 3 category 1 and 2 category 2, then if a point ends up in that, we will give it category 1, to give it the maximum category. So for each tree in this bag, we can figure out what is the predicted category, and then again we'll just take the majority prediction. So there will be a category that's most that has the most votes, and that's the one we're going to take. So this is a bootstrapping algorithm.
Sorry, just to try to understand this thing is, so one question here, like the training set has n data vectors. So if we take n elements out of which, then we'll be repeating the same data sets all the time.
For instance, you can make a tree where you draw the same points n times.
Okay, I see.
They will give you a tree that was pure right away.
Right.
But you can have repeated, the same point can be repeated many times in the data set, and you can still make the tree.
But wouldn't the tree will be the same? Like if we have the same data points all the time and it's the same algorithm?
No, because they won't be the same data points. It'll be different. I mean, it'll be the same data points would appear. I mean, but if you, as I said, if you draw the one sample you could draw would be the same points capital N times. There will be a sample from with replacement, right?
No, sorry, I think I'm missing one thing. Because a training set has n points, n data vectors, and from that we are picking.
Okay, so here's how you make it. How you draw? You draw 1 point and keep that, and then you put.
Oh, I see. Okay. Sorry, I got it. Yeah. Okay.
Okay.
Yeah.
And so for each, so you can do this almost as many times as you want.
Yeah.
And then for each of them, you make the tree, and so that gives you a large number of trees, or depending on how many samples you draw. It gives you a number of trees, and you take a data set, and you take a data point, a new point, and send it through all these trees, and each tree will predict a category, and then you take the majority vote of these, and that will be the category you assign to the point.
Okay.
So that's the bagging classifier. And another and more sophisticated variant is a random forest, and that's in some sense is pretty much the same. It uses bootstrapping also, but you have a different methods to construct the trees, and it does the resampling in a more advanced way, and it also takes out it samples the features, and so it resamples features also. So it's a more sophisticated way of doing bootstrapping. So I'm not going to go into the exact algorithm how to do that, but that's what the random forest is, and that is a pretty popular classifier that seems to work fairly well. So right, so here's a little bit of code that does the bagging tree predictor, and here's the same data set, but we're using a bagging with 1,000 resamples, and so we can see here that the decision boundary we get is slightly different from what we got before, but not too different. Random forest is also built into SKlearn. You can do that too, and here's the that was the same thing. Sorry, that should have been a random forest. but I guess I did it. But you can use the same. You can use a code that there's this piece of code that draws a decision boundary, so it draws the regions it divides into. You can try that with a random forest too. So that's the decision trees is the basis for these two, bagging and random forest, but also for some other very interesting methods called boosting, and they seem to have worked very, very well in a number of these competitions that you have on Kaggle. You have all these competitions on who can design the best classify, and their boosting methods, in particular gradient boosting, which we won't talk about, but we'll talk about adaptive boosting, or ADA boost, next time. That's also a fairly useful method. Okay, so Adam, are you?
All right, I'm here. Before I get started, just a historical comment. So trees was invented by a man named Leo Bryman, who's I think one of the more interesting and better statisticians of the latter half of the 20th century. And he improved it, and he eventually came up with random forest. He called it the best off-the-shelf modeling system in the world, and you know, it's great stuff. And before I get started, one other point worth making about, you know, Niels was talking about classification and using trees for that, but you can just as well use trees with numerical data, and instead of trying to get classification, try and get a number. I mean, in essence, what you're doing with the tree is every time you're trying to make the nodes look more like each other. So, you know, a measure of, for if you have numbers rather than, you know, labels, you can just use, you know, sort of the variance or the standard deviation, you know, as a measure of impurity, if you will. So, for example, if you had a node and all the values are the same, the standard deviation is 0. If the values differ a lot, the standard deviation is going to be large. So the exact same thing works, and in essence, all you do is you change the loss function. And for numerical vectors, clearly the clearly distinct favorite is to just use variance or standard deviation. They're obviously the same as for that, and then you get regression trees. And I mentioned this. Sorry?
You can take, I mean, if you have values, right, you can take the mean squared error instead of the
the variance, right? That's
right. Yeah, okay. Well,
yeah. So maybe that's a good way to put it. Is, you know, the variance is another way of saying the mean squared error between, you know, the average value of the all the numbers in the node, and, you know, well, that's what it is. The mean square error is, you know, the difference between the average value and the actual values, mean squared, and we'll see that in a second. But so you get regression trees, and they work the exact same way. Everything Niels said is true. The only thing is, your measure of impurity becomes, you know, means, you know, variance or mean square error, and you can do the exact same thing. And having said that, I want to share my screen. And which one do I want to do? I think it's this one. I think we're, this is it. I think I just need to, yeah. So it's called a bagging example. I just like that. So we're going to go back and look at the Boston housing data set. And next week, I'll go through a full-blown example. I'm not going to use the Boston data set, but I'm going to go through a full-blown example of using Caret. In some sense, this is a bit of Caret light. Okay, so one question you can ask is, so in R, there's various packages for trees, and there's one called tree, which is the one I'm using. And I don't know if that's the best one anymore. I think some people say our part is better, but as Neil said, trees are the basis for some more sophisticated packages where you look at random forests or you look at boosting of various sorts. And these outperform trees almost always. And the reason is because the models that trees produce tend to have higher variance. And one thing people liked about trees is you have this splitting. You know, you can sort of say, I understand what's going on. I'm going to take this, and you know, if this happens, I'm going to do this. And it's very easy to understand. But with really big and complicated data sets, the splitting just becomes so complicated and so many splits, it's not really intelligible. Incidentally, another piece of history, trees were invented by Bryman. He was asked to solve a specific problem. A hospital said they had data of patients who had heart attacks, and the question was asked, how can we decide which patients are at the greatest risk to have follow-up heart attacks? And they had some data of patients who had heart attacks, and they used that to produce the tree of, you know, decision based on various factors like age, you know, systolic blood pressure after the event, and a few other things. And they came up with a decision tree that was actually used in the hospitals to decide who were the patients who were most in need of follow-up care. Okay, so we just want to see, I want to show you, and this is R, of course, not Python, but it's very similar, how...
you can also see if you can survive the Titanic disaster, right?
Okay, so the Titanic disaster is the quintessential Kaggle demo program. And I think you can use trees, but I think random forests and boosting work much better for that too.
This would classify us all as being dead, right? All of us here at the...
I think most classifications say that you and I, Niels, do not make it. But the one thing we have going for themselves is the reason why the elder white men didn't live was because they were gentlemen and they gave up their spots on the boat to women. I won't speak for you, but you know,
the first question,
you have to be special.
The first question in the tree is, are you a man or a woman?
Right.
If you're a man, you end up pure dead. That's
very few men survive, yeah.
Yeah, right.
Okay, so I'm just going to, this is just showing you loading the packages. And it's going to use random forest, which is a good package for random forest. And whatnot. Okay. So remember, let's just go about it. The Boston data set is information about various zones in Boston. And the predicted variable you want to track is medieval, or, well, some people say it's medieval, but I think it's median value. It's the median value of a house in the zone. And you have all these different factors. And you have the crime per capita. You know, the zone is proportion of residential lot zone for lots over 25,000. There's a dummy variable for all you near the Charles River. And you can see, just, I don't want to waste our time by going over these. If you're curious, this file has been uploaded and you can read them. But there's a bunch of different numbers that, you know, relate to how you might value a property. So we have that, and we want to predict the median value of houses. So you may recall regression worked pretty well, but not great. Let's see if these things are better. So the first thing I do is I'm just going to divide it into a test train, and I almost always, if I have no reason not to, use 70% for training, 30% for test. So I did that. So if you're doing it in R, there's, you know, I'm always happy to point out problems with Python, but I think it's fair to point out the problems in R too. So R has one huge syntactical issue associated with linear model syntax, and that is so the command to create a tree is called tree, and you use the same syntax of I want to compare median value. The tilde dot means to all the other variables. My data set is Boston, and I'm going to use a subset called training. And if you do that, you'll get an error message. And if you're very familiar with R, this says that the error message is a big hint of what's going on. It's looking for some sort of list, and you haven't given it a list, you've given it a matrix of data things. And this is typical for LM, but not so much but it doesn't happen in caret. The function it's what it really wants is an index when it says subset. It wants the index of the subset, it doesn't want it. So that's the problem. And it's easy to solve. I don't like to give it an index in case I want to do other things with the training set or the whatnot. So the solution I have is I use the tree function. I want to compute median values to all the other variables, and I'm just going to give it the data set that's the training set. And then I'm just call that tree.Boston. And my predictions, I just predict now works just fine. I want to predict with my model it's called tree.Boston, and my new data is the test data. And I can plot that, and you can see that it's not perfect, but it's predicting roughly an equal number above and below. So it is doing that, and Niels mentioned the mean square error.
Adam, like the one where you got the error versus this one, what's different? Like I see you still have tree and you still have train. What's different between this?
The difference is, okay, so if you go back, I said compute tree with the same formula. I said use the data Boston and just use a subset of train data.
Okay.
So this is saying create a tree for the median value against all the other variables using the Boston data, but take the subset that's trained. Whereas the more direct thing is to just say, I want to create a tree. I want to predict the median value against all the other variables. And my data set is the data set I call train.
Okay.
Okay. And then the predict function then works nicely. I created this object called tree.Boston. And I just say, all right, predict with the new data, which is the test data. And then I just plotted it over here. You can see it's working pretty well in the sense it's an equal number above and below. And then I computed the mean square error. So the tree in the end gave an error of it was off about $5,000. Right. Remember that the median value was in thousands of dollars. If it was really off by just $5, wow. Okay, so I said it did better than regression, but it's 2 lines of code. Let's just do it. I mean, I can do the linear model. LM is the command for linear model, and it's the same thing. My formula is I want to compare median value. I want to predict median value with all the other variables. I give it the trained data set. I create this linear model. I throw it in the predict function. The new data is the test. And I want to see how that compares. And I see it's slightly worse. About 5% worse. So there is improvement to doing the tree over the linear model. So I think at the time we did that, people thought the linear model was pretty good, but we see an improvement. Okay, so I'm going to compare the linear model and the tree, and we're going to do random forest and boost. As Neil said, bagging is when you look at subsets of the data. So you just take sample with a replacement. So the key to that is to take a sufficiently large number of samples. If you resample once, you could, as Manish pointed out, been incredibly unlucky and just pick the sample that was one data point repeated however many times you originally had, and that's going to give you a really crappy model. But if you do enough trees, you're guaranteed that these things will average out. And so the point about doing bagging is it will reduce the variance. As I said, trees tend to be high variance, and bagging is a procedure that will reduce variance. So I want to, for various kinds of models, I have the predict, my predictions. I'm just going to compare that to the MSE and do this. So I'm going to create a matrix to do that. So I'm going to pre-populate it with zeros. I'm going to have 6 rows because I'm going to in the end do 6 models. I'm going to have 3 columns of data. because I'm going to have, as you can see here, the mean of the test value. So what's the average value of the houses in the test? What's the average value of the prediction? And what's the mean square error of the thing? So, and that's predict comp, I'm just calling that the name of the matrix. It's of zeros with 6 rows and 3 columns. And I'm giving it the row names of what they are. I'm going to compare the tree, bagging with 250 resampling, bagging with 500, random forest with 250 samples, trees done, and random forest with 500, and finally boosting. And I'll talk more, I'll add to Neil's discussion when we get there. And I'm just going to, as I said, just look at the mean of the test housing values, the mean of the predicted values, and we look at the mean square error. And, well, the first column we know, it's just going to be the mean of the test for everyone. So I can make the first column just be, I just want it to be that same value. So I want to round it to 2 decimal places for neatness. So I'm going to make a matrix with the mean values, and I'm just going to have 6 rows 1. And you can see there it is. I've pre-populated the mean of the test is. I'm going to have to add in these other values a few times. So let's write a function to do it. So I'm going to have 2 things. I have the test values for the median housing, and I'm going to have my predicted values y hat. So I want to create a matrix that'll give me 1 row. So I'm going to make a matrix of zeros, 1 row, 3 columns, 1, 2, 3 columns. I'm just going to run on all these different things. And the first one, I'm just going to, I didn't need this duplicative, it's just the mean of the test set. Then I'm going to take the mean of the prediction. And finally, I'm going to compute the mean square error, which is the square root of the average of the difference between your prediction and your actual quantity squared. And return out, by putting that last line, I didn't actually need return. That just means if I run it, I'll actually see the value. Okay? Are there any questions on any of this?
Matrix 0, 1, 3. So 1 row and 3 columns. What is the first component 0 in that matrix?
No, that means it's all zeros. So if
all zeros. Okay.
Yeah. So you have to give you 3 pieces of information to create a matrix.
Yeah.
What the values are.
Yeah.
Right. How many rows and how many columns. I mean, it doesn't have to be constant. For example, I could just say, so the rnorm function gives you random normal values. I could have had rnorm 3, and it just would populate it with 3 random values. It's good to when you're pre-populating, when you're instantiating a matrix like this, it's good to pick a value that's easy to see and is unlikely to occur in real life, so you can see if you have a problem.
Yeah.
So when I'm done, if I see a bunch of zeros over, right now I see zeros, but if when I'm done I see zeros over here in these 2 columns, I know there's been a problem. All right. Okay, so this didn't correct. It should be what is out of 3. And the question is, why isn't out of 3 just y hat minus test? I will show you that. Where is it? Okay, out of 3 was the square root of the mean of y hat minus the test, the prediction versus the actual value. You add those, subtract them, square them, take the average, and then take square root. And the question is, why am I squaring and taking square root? And, there's too few people here to formally do tests, but so people should just shout out what they think. And the answer, my 3 choices, that will work too. Second answer is that's just a different way of looking at 3 things in 3. And I think I know which one Neil is going to go for. This is just the standard error. So
why am I taking squaring and taking square root? If we don't square, then it will be plus and minus. It will go to 0, right? So
absolutely, that's why you square them, and then you take the square root because you want to have the same units as you want to have. Yeah. So this is just standard L2 error. Okay. So, oops. So recall, as Neil said, that bagging is where you take the data set and you sample with replacement, and you use that to train your model. So if you did it just once, it can be very screwy. In particular, as I recall off the top of my head, I think it's 63. On average, you only use 63% of the data. There's only 63% of the data points are distinct in any given bagging sample. That's the expected value, to have 63% distinct. So you need to do it a bunch of times. And I'm going to use the random forest function because what random forest does is it not only randomly selects the data points, but at every split, rather than considering all the possible criteria, it only uses a specific subset of, a specified number of subsets. So in other words, it randomly chooses the data, and at every split, it randomly says, rather than splitting on all the possible variables, I'm going to pick a random subset of those. So if you do random forest, but you say, I'm going to, the number of variables to use for the split at every time is all of them, you've recreated bagging. Is that clear?
No, sorry, could you repeat once again?
Yeah. So random forest adds another. So if we didn't have this mtry, okay, and we'll talk about importance in a second, this would just be bagging. It would just say, compute the median value against all the other variables. My data is try, and it's just going to bag the data set. What random forest does is it says, at any given split, you pick a specific number. So let's say there were 100 variables, mtry 13. You say, randomly pick 13 of the variables and only use one of those 13 for the split. Remember, all these things are looking at all the possible places you could split with all the possible variables to find the one that gives you the maximum reduction. Okay? So when you use random forest, it says don't use all of them, just use a subset. So in fact, if you had a photographic memory, or take my word for it, there are 13 independent variables. So when I say mtry equals 13, I am saying use all the variables at every split. So I'm not doing a real random forest, I'm just bagging. Okay? So this is the formula, and importance equals true. Well, first of all, n-tree equals 250 means I'm going to do it 250 times. I'm going to sample my data set 250 times, compute 250 trees, right? Now remember, each time, in fact, it's looking at all the variables, and at every split is picking the one that gives the maximum decrease, not of entropy or a Genie index, but the maximum decrease in the mean square error in the nodes, okay? So one thing you could do is you could keep track of it. You could keep track of, at every node, on every tree, what variable you used and how much, in fact, did it reduce the mean square error. So it takes a node and it divides it into two nodes. And the one thing you know for sure is that the weighted average of the mean square error of those two nodes is lower than the node above. So you can say, well, what variable did it split, right? And what's the difference between the weighted average of these two mean square errors compared to the mean square error of above? And you can keep track of that. And obviously, if you're picking at any given node, you're picking the one that does the maximum, but you keep track of, does some variables lead to really large reductions in mean square errors, whereas others don't lead to such significant differences. So this importance equals true says keep track of that. Okay. So then, but I do run it. I create this model, which is 250 different trees, and then I can run predict on it. And my new data test as before. And then I remember the comp out function simply just tells me, in essence, it's computing the mean square error between my prediction y hat and my actual value, which is test.mdv. And now I can put this in the second row. And now, lo and behold, I mean, obviously, I don't know, that's weird. I must have done something. Oh, I forgot to write round in it. So this is not showing the same, because 22.50658, when you round it to two decimal places, which I forgot to do, it can be 22.51. Okay, but you can see the predictions are well, a little closer, but more importantly, the mean square error is going down. Okay, so it's not it's a reasonably significant difference from $5,000 to $4,000 by using bagging as opposed to using a tree. And this is the variance averaging. This is exactly where you're seeing the variance averaging come into play. You know, you might have gotten lucky with one tree or not lucky, and of course we didn't do all the details. Trees should be pruned, but by averaging over 250, we improve. So I said the variable importance tells you how much it did. So let's see. So this shows you for each of the variables the percentage increase in MSE or decrease that you got from these variables. So looking at these, you can see very clearly that the most important predictor in the random forest was the number of rooms. It had the, it gave a, 45% of, if I'm reading this correctly, well, essentially 46% of the decrease in MSE you saw over all the models came from rooms. Unimportant variable? Well, there's two things I think that are interesting. Well, first of all, it says Charlotte being near the river wasn't important. The next least important one was the zoning, whether it was industrial. Tax was somewhat important. I forget what DIS is. Let's go back and find out. Weighted mean distance to the 5 Boston employment centers. So that makes sense. You're close to work. That made housing more variable. And I don't remember LS stat either, but you get the idea. But even nicer, you can now get charts of this thing. And
what was the second column? Like node purity? What is this one?
Sorry?
What's the second column? Node purity?
Node purity is just a different measure of well, honestly, I just use MSE. Okay. I don't remember. I could look it up. But increased node purity, it's some other numerical measure of by what percentage, how much you got to nodes with just the same value by using those particular variables.
Okay.
I don't remember, honestly, I use MSE myself. I forget what increased node purity means. I can look it up if you're curious.
Yeah, I think there is some difference between the two definitions of weights computing, because 11% P ratio translates to 447 and 8% crime translates to 808. So it's not like one.
No, they're not exactly the same. You can see this is about 100 times larger, and this is 15 times larger. This is 6 to 140 is 25 times larger. So they're not the same.
So Professor, this increase in MSE is across all the 250 trees would be.
This is measuring over all the trees.
Yes.
The point is and that's the important. That's very important that it doesn't just pick which tree it thinks is best. It looks at all of them to get some sort of average. In some sense, by going, it's reporting a gross amount of reduction. But since you're going over so many trees, you don't fall victim to overtraining on one particular data set. Because these trees, look, in this set, as I recall, there were 700 different zones. So once you get to 700 nodes, you can always split it so each node has just the one value, and then you're perfect, right? But if you use that tree, you're going to do perfect on your training data, but you way overfitted, and it's incredibly reasonable to expect that when you go give it new data, you're going to see very bad results. So when you train on 250 different data sets, if you will, it gives you a chance to, to see different sets of circumstances and reduces overtraining, which is to say it reduces variance in the predictions. But this is a nice feature, and Niels, I'm sure, is going to give you exact definitions next week. But this variable importance is one of the really nice features that you can see once you do ensemble models like bagging. Okay. Any other questions? Okay, next slide. Okay, we're going to repeat this now with 500 iterations. We're going to, sample the data set 500 times. And the question is, do you think this is going to improve things? And the three choices are yes, no, and maybe.
Yes.
Chaos, do you want to guess?
Yes. It should be yes.
Niels?
Maybe.
I'm with you, Niels. Maybe. It probably will. But, I mean, you do have the issue that you could run into overfitting. First of all, you could be unlucky. But but the other thing is now 500 isn't nearly enough. But if you took 10,000, you would definitely overfit. And then you probably wouldn't increase things. But I'm going to go maybe or, usually. But, as I say,
It's always the safest. Maybe is always the safest choice.
Maybe you're right on that. I don't know. But let's do it. And when we do it, we see that the bag RF, it improves the mean square error, but very, very slightly. Okay. So the only difference between the two formulas is I've gone, oh, wait, I didn't say how many times to do it. And that's because it turns out that for this model, it defaults to 500. So if you don't tell it, it just automatically gives you 500 trees. So let's move on. So random forest, the difference is we're not going to have m try equals 13. Okay. Now you can, if you were in a situation where you're using caret and you really weren't sure, you could, make this one of the variables that you wanted to tune on. You can make this one of the hyperparameters. And you could say, try, 2, 5, 7, 10, and 13, or whatever you want. The random forest, there are sort of empirical defaults for what you should do based on whether you're doing a regression trees or categorical trees. And if you don't tell it, it will pick for you. So I'm just going to do this. So I'm going to not tell it. So I'm going to let it, and I think it's P over 3. So it'll take 4 or 5 trees at every split. And I'm just going to run the random forest function, which is the same function, same formula. The only thing is I'm not forcing it to use all the trees. And so I'm going to, everything works just the same, predict, and then I use my function to compute MSE and populate the other 2 elements of the row. And then finally, I do the same thing for 500 trees. And we can see that once we go to random forest, we improve again. But when we go to 500, maybe we are hitting overfitting, or maybe it's a statistical aberration. But it's better, but this is claiming that the 500 doesn't actually improve. And the one thing I was kind of curious to see was, did when you did the bagging versus when you did the random forest, did it change what variables were important? So here I had the importance of the 500 bags and the importance of the 500, and I just compare them. I'll push this down here. We can see, and let's just look at MSE, and we see again that rooms, the number of rooms is the most important one. It's 55%. But when we go to the random forest, it's still the most important one, but it becomes less important. It goes down to 33%, which suggests that, maybe the reason why the model is doing better with the random forest is because it's relying less on the number of rooms and more on other factors to determine what it does. So what's gone up?
The industrial area.
Yeah, industry has gone up.
Crime is free. Yeah.
Crime a little bit. Yeah. So it's, kind of interesting to, to compare them. And finally, Niels, we haven't really talked about this, but boosting is a very interesting method that usually involves trees, and that's why it's always good to understand them, even if you're not going to create tree models. But I did do just one simple model. And to give you an idea how long ago it was that I did this, I use the gradient GBM function, which means I use the GBM package. The GBM package has since been orphaned, which means the developer has said, I'm not going to work with it anymore. If there's any problems, I don't care. Leave me alone. I have no interest in what happens to it anymore. And the reason why is because people using, you know, ideas from gradient descent, and in fact, actually the Newton method, and I'm bet money that you're going to hear lots of interesting details about this next week from Niels. They discovered that, you know, you could use the Newton method very effectively when you were doing boosting, and you could much more rapidly produce results than you would with gradient descent. And so traditional packages like GBM, which used gradient descent to compute things, went by the wayside because XGBoost using Newton method appropriately were just much faster. But in any event,
Light GBM, right?
Sorry?
Light GBM.
Light GBM. Yeah, Niels likes light GBM. I'm old-fashioned. I'm still an XGBoost guy. But you mainly claim that light GBM is much easier to install in Python, right?
Yeah.
Yeah. For our both packages are very easy to install. There's no problem installing either.
Well, it's if we want to use GPUs, it's XGBoost is a little harder to install.
Yeah, I did actually, you know, read something, you know, about a guy did some very extensive testing, and it really depends on what kind of, if you have lots of CPUs, certain programs are better. If you're using multi-nodes, others are. So it's very interesting, you know, that there's no such thing as the best boosting package. It depends very much on your hardware. But these are all orders of magnitude, literally orders of magnitude faster than gradient boosting. But in any event, it does use the same formula. I'm going to compute median value versus train, and that's just telling it I want regular numbers. I'm going to, yeah, this would take a while if I ran this, but I did run it, and I get, this is, you get a much nicer variable importance chart. But it does still say that room is the most important one, the number of rooms. Okay. I did, then I did a test on a bunch of them, and I, yeah. For some reason, I don't seem to have computed the MSE of the gradient boosting, but maybe I can do that very quickly. It does improve. Hold on a second. That's not what I want. Okay. Oh, no, I can't. Oh, hold on. I'm just going to tell you in a second what it was. Okay. So when I just did that very simple one, actually the median square error went up significantly. How do I resume? Okay, resume share. So I don't have it here, but it actually was worse because I didn't very intelligently choose the hyperparameters. But I promise you that if you do choose them properly, you will get them down. I think I want to say that I got down to 2.8 or 3, so about under $3,000 for the mean square error when I properly tuned the boosting.
One question here.
Yeah.
In bagging, as you increase the number of trees, you're saying that you have more chances of you will be increasing overfitting. Is it because every time you create a new tree, but still it will look at the majority and decide the
It's an average. You would have to take way more trees than 500 to get overfitting.
right? But I'm just wondering, like, if let's say if you have 2,000 trees or 10,000 trees, why would that create an overfitting scenario?
I think in this case, no, but if you took like 50,000 trees, I think you would probably get into the realm of overfitting. I mean, you could do,
No, I'm just trying to understand, like, theoretically, like, by increasing the number of trees, why the chances of overfitting is becoming bigger?
okay, so the way we created these trees, any given tree will certainly overfit, right? When you create an average of the trees, you're decreasing the average fitting because you're decreasing variance.
Right.
I mean, by bagging the data set, you're creating, you know, if not completely independent variables, but, you know, reasonably uncorrelated variables, right? So at some point you run into the issue of the variables are no longer uncorrelated. At that point, I mean, imagine if you created enough models, so essentially you got there was excellent chances that you were getting data sets, some data sets with just a few examples. At that point, you would probably start running into overfitting. I mean, but I do it, you know, I mean, it was from 250 to 500 or even 5,000 or 10,000. You know, it would be very, very bad luck if you overfit. And you can overcome this bad luck very simply by just rerunning the whole process of producing 10,000 trees, you know, a few times. So for example, you know, it takes almost no time to run 5,000 trees. And in R anyway, in our studio, any session uses one core. So if you wanted to, you could always just sort of, you know, let's say you had a double core machine and, you know, so you have 2 threads per core, you could run up 4 instances of our studio and do 4 of them and then be almost guaranteed. And, you know, actually you don't even have to run up 4 instances. There's, you know, par 4 loops and various other ways of, you know, parallelizing things in R. So. But yeah, no, I mean, to vote, I mean, it was a bit, it's not facetious, but it's really just 500 trees is vaguely beginning to be enough trees to create problems. You're right about that. Just, as Neil said, maybe is always safer.
Well, you can see it. I mean, in random forest, if you take a very large forest and you look at the decision boundary, you get something very jagged, which is an indication that you're overfitting, right? So you get a lot of little nips and cuts in the decision boundary.
Yeah, I'm having trouble hearing you, Niels, but I assume what you're saying is, I heard the part about jagged boundaries, and jagged boundaries, as I'm sure you were trying to say, always means overfitting.
Yeah, often. Right. Yeah. But that's what you can see. I mean, you can if you experiment and try to take very large bagging, a very large random forest, you'll see that you get very jagged decision boundaries, and that's is definitely an indication of overfitting.
Yeah, great point. All right, I think I just did one more thing where I took a look at a large selection of I must have just run the code. I seem to have, instead of see. Oh, I see what I did. When I wrote the code, I forgot to take square root. So hold on a half a second. I mean, so, oops. So these numbers are the squares of what you want. Where is that? It's over here. So, hold on. 20, 1, 2, 3, root. Yeah, so, what did I have? Yeah, I don't know. The only thing I can read from this that I believe is that all these models relatively independent from 1,000 to 6,000 trees. They gave you about the same error.
This question is for MSC calculation. Won't you need y hat minus test $mdev MEDV? Why it's just y hat minus test?
That's why it's giving you these weird numbers. It should be test $MD $ median value.
Yeah.
That's why it's giving you these weird values. It's what we call a typo. I think that's the technical term for it. But if you change this test to test dollar, oops, it would give you the right thing. If you want to wait a half a second, I can't share. Well, hold on a second. Let's see. Yeah. Okay. So what I'm going to do is stop the share and give you a different share. Share. Where is it? I think it's this. Yeah. Yeah. So if I go in here and change this to test $MEDV, now it'll take
Square root.
a little bit of time to run this because I'm running it over.
And you also need to take square root of that.
You know. SQ root. Okay. I think those are the two only errors I could make, and I did make them. I think this takes like a minute or two to run. Obviously, what takes time is when you get 4, 5, and 6,000 trees, and I'm
So one may ask, like, if boosting is predicting better, and we see that tree-based methods
typically
are
produce
better
best.
than regression. So why one would do linear regression, and why? I mean, what is more important to understand here is that between these methods, what method will work better in a given scenario? What is the scenario where you may want to use just linear regression versus when you want to use probably tree-based method? I mean, I understand lasso and ridge because they avoid overfitting, right?
Yeah.
But when it comes to comparison between lasso, ridge versus tree-based method, which one will one pick?
Let me make sure I understand your question. Your question is, I understand the point of using ridge and lasso is it will reduce overfitting. Why use these models?
No, I'm saying that these models looks very effective, but the question is, would it make the other models useless? Because if these models are reducing MSE by such a big margin, then people will always use these models, and they will not use lasso and ridge.
I see, yeah. So why use lasso, ridge, or even linear modeling when you have these things?
Correct.
So there's, to me, that I answer that, and I'm curious to hear what Niels has to say, but my answer is two parts. The first part is for many things, they are used. Like, for example, in the Kaggle competitions, and in, most serious machine learning problems where people are producing models, they're not using regression anymore.
Yeah.
But why would you ever use regression? You could see how much longer it took to run this than it did to run, just even the basic tree model, let alone a linear regression. So there are times when speed is an issue.
Okay.
And so if a linear model is fast enough, is reasonable and much faster, there may be times you prefer. Along the same lines, you run into issues of explainability. People love linear models because they understand them.
Okay.
Now this information is 5 years old, and maybe it's changed. But I knew a guy who worked for a consultancy, and they did work for insurance companies and hospitals and whatnot. And these hospitals would let them use like logistic regression, would occasionally let them use trees, but wouldn't use any more complicated models because they weren't happy with them because they couldn't understand what was going on.
Yeah.
And for example, in credit scoring, banks, for example, it's the law. They can't just say, we ran a model, you're a bad risk. You have to be able to explain it. So there was a long period of time where banks were using logistic regressions, and because they knew these other models were better and would give better predictions, but they weren't allowed to use them because they didn't know how to legally justify them.
Yeah, but then still,
but you know what? Like, all right. So you're in finance, and I presume you guys do a lot of regression. One thing the problem with these models, I think, in finance, is they're not going to work for high frequency. They're too slow. But maybe guys have figured out how to make them faster and are using some of them. I don't know. But when and the problems that I've solved, I think almost always, if time wasn't an issue, gradient boosting provided the best solutions.
Okay, it looks pretty good, 3.6.
You can see the wide range as you go from, not a lot of iterations, and not a lot of models, not a lot of depth, and not a lot of trees, down to a lot of trees and a lot of depth in the model.
But is it true that these methods would always provide better results than logistic regression, or?
Usually, suppose your data is actually linear. This isn't going to be any better.
Right.
Yeah, I think one of the reasons also is that people know how to do statistics on linear regression, and it's not so easy to estimate risks and uncertainty in these other models. You don't have, it's sort of like for linear regression, you have well-developed methods and distribution of the coefficients and stuff.
Yeah, you saw that, granted, I'm not running a state-of-the-art, but this is a decent computer. It's an i7 chip. Now imagine trying to run this model 10,000 times. It took a minute or two to get decent bootstrapping confidence intervals.
No, for
So
sure.
that's a good point.
You can definitely get empirical distributions out of running it many times, but
Right, yeah.
linear regression has been around for a long time, and it's sort of very well, the statistics is very well understood, and this has a lot to do with tradition, right? If you're a drug company and you're going to have to submit something to the FDA, then it has to be in. You can't use machine learning or prediction there. That's not going to work. So they're not going to let you do that. No, I mean,
But I did know some people who are actually in the, not payday loan, but, the online loan business. We'll give you an answer in a minute. And all you're doing is you're getting, just minimum amount of statistics from a credit agency and computing your credit score. And they were all using random forests.
Yeah.
And they were eating the bank's lunches because they were that much better. They could offer still very shitty, but much better, really shitty rates than the banks on credit cards. No offense.
Yeah, no, I think that's true. I mean, on the consumer side is fine, but if you have to submit things to a federal agency to get approval and stuff, then you're going to have to do some kind of statistical analysis that they can understand, and it's an accepted way of doing
right. You can go to a bank and say, we ran a logistic regression and we decided there was only a 20% chance you're going to repay.
Yeah.
But, they were happy with that. But if you said, hey, we did a gradient boosting model, and the gradient boosting, we said you had a 20% chance, they said, what's gradient boosting?
Yeah, exactly.
And then a few hours later, they said, oh, no. That's no way.
On your I mean, if you look at your phones and stuff, it's all using machine learning and gradient boosting and deep learning and stuff. So all this stuff that's going on your phone is.
Okay.
Right.
Yeah.
Yeah, I think great session. Thanks, Adam. Excellent. I think
next week I promise a functional, full-blown carrot demonstration.
All right. Thank you very much.
Okay.
Thanks a lot, professors. Thank you.
So Neil, we can talk about it, about that person on an email. Okay. I also need to send you an email and Adam about something else I thought about. So I'll send you.
Okay. All right.
All right.
Sure. Sounds good.
Thank you.
Thanks.
All right.
Okay, bye-bye.
Niels, I will see you next week, and next week I will see you.
And on Thursday, for sure.
Thursday for sure, and hopefully Wednesday. I'm gonna.
All right. Sounds good.
All right.
Okay.
I'm gonna hang up.